Okay, next let's look at the planetary rings. This is the photo of Jupiter's ring. It was discovered in '79 by space probe Voyager 1, which has now left the solar system. And it consists of very fine dust particles. Saturn has spectacular rings that were observed by Galileo, again, when he pointed the telescope to the skies, when he saw that Jupiter has satellites. And these rings consist of chunks of ice or rocky material covered with ice. And as you can see, they have very high reflectivity, very high albedo. They reflect a lot of sunlight, right? So we can see them quite well. And the chunks in the rings range in size from a ping pong ball to maybe an object of the house. And here is an artist's view. This is not a photograph. It is an artist's view, although there is a probe dedicated to examine its rings. It's called Cassini, after the name for this largest gap in the structure of the rings. So this would be a view that you would have if you were riding on one of those chunks revolving around the Saturn in the ring. They stretch for about 274 kilometers from tip to tip, but the thickness is quite small. It's only 100 meters, right? 100 meters is nothing compared to 274,000 kilometers. So these rings are very, very thin. As I mentioned before, the rings are divided by gaps, and the largest one is called Cassini's division. And the reason for it is one of the Saturn satellites, Mimas. And basically, the argument why there is a ring, why there is a space where there are no particles, is as follows. Turns out that if there was a particle in the division, it would have an orbit that is synchronous with that of Mimas. What I mean is that after half of Mimas' year, the object would actually complete one full circle. So that year of Mimas is twice the year of this object. There is a periodic synchronous gravitational tag on a particle that would be in the Cassini's division, which causes it to be pulled out. It cannot sit there. This synchronous tag by the force of gravity of Mimas actually takes it out. And analogy would be a rhythmic push of a child on a swing. You know that if you push a person or a child just at the right intervals, you don't have to exert tremendous push, but you have to get a so-called resonance condition that depends on the mass of the child and the length of the swing. If you push a little bit just at the right intervals, you can achieve a great swing. So the same sort of thing is happening, and this so-called resonant gravitational pull by Mimas would take a particle that is sitting in the Cassini's division out. Then there are other satellites that cause other gaps, but this one is the biggest, and it's quite easy to understand the argument for its existence. Okay, here is Uranus with its rings, which were discovered in 1977 by star occultation, right? As they move together with Uranus, a distant star would be covered by the rings, by the thin ring. Its brightness would go to 0. So that's how it was discovered in 1977. Of course, later, better images were obtained. Since then, 9 very thin rings were discovered by Voyager 2, and they are not bright as the rings of Saturn because they are made up of dark material with low albedo, right? They're not, clearly not as bright as the rings of Saturn. Okay, and here is Neptune with its rings. And it was first discovered in '84, and then in '89, Voyager 2 found several thin, non-uniform rings. So the question is, why do the rings form? How come that this material did not coalesce to form yet another satellite of Jupiter or Saturn or Uranus or Neptune, right? Why do we have rings? Remember that the tidal force increases with decreasing distance. The closer an object, a satellite, is to a planet, the greater is the tidal stretching force. And there is something that is called a Roche limit. It's the critical distance from a planet within which the tidal force on it would break it apart. So if a satellite is far enough from the planet, the tidal force is not great. It will have probably nearly spherical shape. But if it gets closer, it will be more deformed by the tidal force. It would be more stretched. And then if it reaches this particular distance from the planet, it would be broken apart into bits and pieces. Now, if you remember the so-called Keplerian rotation curve, right? The speed squared of a body revolving around the other body decreases with distance as 1 over the distance. So the smaller the distance, the higher the speed. So these pieces that are within the Roche limit would be moving faster than the pieces that are outside. So this difference in speed would spread the material and would form a ring, right? If there was a satellite that for some reason crossed the Roche limit, it would be broken apart by the tidal forces, and then pieces closer to the planet are moving faster than those farther away, and this difference in speeds would actually result in a ring formed around the planet. And it turns out that for a body that is held together only by its own gravity, which is not the case with artificial satellites that we launch and use for communications and so on and so forth. They're not held together by their gravity, right? They're held together by mechanical elastic forces. But if the body, like typically satellites are held together by their own gravity, then it turns out that Roche limit for a planet is approximately 2.4 times the radius of the planet, okay? So here, the Roche limit would be about 2.4 times the radius of the planet. And it turns out that actually our moon could not remain in single piece if it was closer than about 18,000 kilometers, right? When the Earth-Moon system formed 4.5 billion years ago, it was a lot closer, but it was at 22,500 kilometers. It couldn't have formed within a distance smaller than this value because it would be torn apart by tidal forces. It would not be possible for it to be a single object. And then if you look at Jovian planets, it turns out that Jupiter's ring is at 1.8 times the radius of the planet, well within the Roche limit of about 2.4 the radius of the planet. So clearly there was a body there that actually just got ripped apart by the tidal forces, and debris formed the ring. If we look at the Saturn, its rings are between 1.1 and 2.5 times the radius of the planet. Again, within the Roche limit for Saturn. For Uranus, 9 thin rings lie between 1.5 and 2 times the radius of the planet. And for Neptune, there are 4 thin rings between 1.7 and 2.5 times the radius of the planet. So clearly, all the rings of Jovian planets are within the Roche limit for those planets.